Every year, the world extracts over 8 million tons of gray, unremarkable ore. But only a tiny fraction of it undergoes an incredibly complex, almost alchemical journey to become a metal capable of withstanding even spaceflight. Titanium isn't just a metal, it's a substance born in hell from fire, chlorine, and magnesium at temperatures exceeding 1,000 degrees Celsius. Its first form looks like light ash, but from it they create the invisible skeleton of aircraft, eternal implants, and rocket engines. How does a chunk of dirty rock transform into a material stronger than steel, yet lighter than aluminium? Watch to the end, and you'll see how an ordinary stone passes through chemical purgatory to become the heart of modern civilization. The history of titanium is the story of a ghost metal that remained hidden in plain sight for decades. In 1791, British clergyman and amateur geologist William Gregor, while studying black sand on the Cornish coast, discovered traces of an unknown element within it. But only 4 years later, in 1795, the great German chemist Martin Klaproth independently discovered the same element and named it titanium, after the mighty titans from ancient Greek mythology. However, despite its thunderous name, the metal remained elusive. For nearly a century and a half, it slumbered in chemistry textbooks, resisting attempts to isolate it in pure form. Only in the 20th century, thanks to breakthroughs by American chemist Matthew Hunter and Dutch scientists, did humanity finally manage to touch pure titanium. From the mid-20th century, with the onset of the Cold War and the space race, titanium transformed from a laboratory curiosity into a strategic material. The United States, recognizing its colossal potential, invested enormous sums into its production. Titanium became the foundation for the legendary spy plane SR-71 Blackbird, capable of flying at the edge of space, and found its place in the construction of Apollo spacecraft. Titanium production begins with mining its ores, ilmenite and rutile. These minerals are found in the sands of Australia, Canada, and South Africa. After extraction, the ore undergoes multi-stage enrichment. It's washed, screened, separated from waste rock using magnets and gravity, yielding a dark, heavy concentrate. But this still isn't metal. This is merely titanium oxide, where it's firmly bound to oxygen. To break these molecular shackles, the concentrate is sent to chemical hell, into fluidized bed reactors. Here, at temperatures of 1,000 degrees Celsius, gaseous chlorine is blown into a boiling layer of ore and coal. A fierce chemical reaction begins. Chlorine tears titanium away from oxygen, forming a volatile compound, titanium tetrachloride. This caustic, toxic substance is then repeatedly distilled, purifying it from impurities to near-perfect purity. The next stage is the heart of the entire process, named after its creator, William Kroll. Into a sealed steel sarcophagus filled with inert argon gas, molten magnesium is placed. Then purified titanium tetrachloride is slowly fed in. A chemical duel begins. Magnesium, being a more reactive metal, literally rips chlorine atoms away from titanium. As a result of this battle, pure titanium settles at the reactor's bottom, but in the strangest and most unremarkable form imaginable. This is sponge titanium, a porous, lightweight gray mass that looks like frozen foam or pumice. It's brittle and utterly unlike strong metal. But inside this ugly porous sponge lies all the future might. This sponge is extracted, crushed, and then pressed under enormous pressure into dense briquettes. And only then is it sent to its final transformation, into the melting furnace. To transform sponge briquettes into a monolithic ingot, they're melted in vacuum arc furnaces. This is necessary because at high temperatures, titanium absorbs oxygen and nitrogen from the air with incredible greed, instantly making it brittle. Inside a sealed chamber, a powerful electric arc, like lightning, melts the briquettes, and liquid titanium flows into a copper, water-cooled mold. To achieve perfect uniformity, this process is repeated twice, sometimes even thrice. The result is a gleaming, silvery ingot of pure titanium, ready for further processing. Just look at this incredible transformation, from porous, lightweight sponge to dense, shining metal. But pure titanium is merely the beginning. To create materials for aviation and space, it's transformed into alloys. To molten titanium, like spices in a chef's dish, other metals are added. Aluminium for lightness, vanadium for strength, molybdenum for heat resistance. Thus is born, for example, the most famous titanium alloy, T6Al4V, which became the workhorse of the aerospace industry. These alloys are remelted several times to achieve perfect uniformity. The next stage is mechanical processing. Giant ingots are heated red hot to make them malleable and sent under presses or rolling mills. With incredible force, machines bend the metal to their will, transforming it into sheets, rods, beams, and wire. From these semi-finished products, the most complex parts are then cut, turned, and milled. But that's not all. In recent years, additive technologies, or three-dimensional printing, have entered the game. Special printers sinter the finest titanium powder layer by layer with lasers, growing parts of such complex geometry that traditional methods cannot achieve. This allows creation of lighter and stronger components for aircraft and rockets, saving up to 40% of weight. Every finished part undergoes the strictest control. It's X-rayed, scanned with ultrasound, checking for the slightest internal defects. In aviation, titanium has become indispensable. From it, they make up to 15% of a modern passenger airliner's weight, landing gear, wing elements, and of course, engine components. This significantly reduces the aircraft's overall mass and increases its fuel efficiency. In the medical field, roughly 70% of all implants, such as artificial hip joints or dental prosthetics, are made from titanium. Its unique biocompatibility means the human body doesn't reject it, allowing bone tissue to literally grow into the implant surface. This is a metal that becomes part of a person. Thus, having passed through fire and chemistry, an unremarkable stone transforms into high-tech material that pierces the heavens, explores space, and restores people's ability to move. But titanium conquered not only the sky, but also the darkest ocean depths. At the height of the Cold War, Soviet engineers created something unthinkable: submarines of Project Lyra, known to NATO as Alpha. Their hulls were made entirely from titanium. This allowed them to dive to depths unreachable by the enemy and develop underwater speeds exceeding those of torpedoes. These goldfish, as they were nicknamed for their incredible cost, became underwater phantoms, invulnerable to magnetic detectors and capable of escaping any pursuit. Titanium is the only material capable of withstanding the colossal pressure at depths of 800 meters whilst remaining sufficiently light. Moreover, its absolute resistance to corrosion in salt water makes it an eternal material for the marine element. So what's titanium's main secret, promised at the beginning? It's not just its strength or lightness. Its true magic lies in its ability to self-heal. Every time titanium's surface is scratched, it instantly reacts with oxygen from the air or water and covers itself with the thinnest, invisible, yet incredibly strong film of titanium oxide. This is a sort of invisible armor that instantly regenerates when damaged. It's precisely this film that makes it absolutely inert, preventing it from reacting with the human body or aggressive environments. But this superpower has another side, another secret. During mechanical processing, if proper technique isn't followed, fine titanium swarf can spontaneously ignite. This white fire burns at such high temperatures that it's impossible to extinguish with water or sand. Taming titanium is playing with fire in the literal sense. And only those who've mastered this art can make this mythical metal serve humanity. Every year, the world produces over 500 billion glass bottles. If you line them up in a single row, they'd wrap around the Earth more than 3,000 times. These are mountains of gleaming, fragile material that could remain in landfills forever, forming glass deserts for thousands of years. But a portion of this material gets a second, third, 100th chance at life. How exactly does an ordinary lemonade bottle, tossed into a recycling bin, pass through fire and mechanical hell to become crystal clear and ready for use again? Behind this lies a colossal technological process that rivals space programs in precision and scale. If you watch to the end, you'll discover the main secret of why glass is called the immortal material, capable of infinite reincarnation without losing quality. And it's precisely this property that makes it a genuine marvel of engineering and ecology. The journey to glass rebirth doesn't start at a factory. It starts on our city streets. Recycling begins with collection. In advanced countries like Germany or Switzerland, this is a well-oiled system where every citizen plays a part. Special containers for clear, green, and brown glass stand on every corner. Moreover, in many European countries, there's a fond system, a deposit included in the beverage price. By returning an empty bottle to a special machine at the supermarket, you receive a voucher that can be used towards purchases. This transforms rubbish collection from a duty into a profitable venture. In other regions, there's an entire shadow army of collectors, people for whom returned bottles are their main source of income. The collected glass flows along logistical arteries, from small trolleys to massive refuse lorries towards recycling plants. It's here, on these noisy and dusty sites, that the first act of its resurrection begins. After tons of glass bottles arrive at the plant, they face their first test, sorting. And this is where technology worthy of science fiction enters the game. Along a wide conveyor belt rushes a motley stream. Clear bottles from water, green ones from wine, brown ones from beer. The human eye can't keep pace with this speed. So optical scanners based on near-infrared technology are installed above the conveyor. A light beam penetrates through the glass while sensors analyze how it refracts. Artificial intelligence determines the chemical composition and color of each fragment in fractions of a second. Color sorting is critically important. Just one green bottle can contaminate an entire ton of raw material for clear glass, giving it an unwanted tint. After identification, the system issues a command. Powerful jets of compressed air shoot with surgical precision at the right fragments, knocking them off the conveyor into separate compartments. But color is only half the battle. Along with glass, the stream contains numerous foreign objects: metal caps, plastic rings, paper labels. Here begins multi-level cleaning. First, the conveyor passes under giant electromagnets. With a deafening clang, they snatch all steel caps from the stream. Then, eddy current separators come into play. They create a magnetic field that repels non-ferrous metals, like aluminum, forcing them to literally jump off the belt into a separate container. After this, powerful fans blow away light rubbish, paper and plastic. And finally, the glass passes through a water cleaning system where organic residue and dirt are washed away. Just imagine the complex journey every bottle we discard takes before becoming clean raw material. After sorting and cleaning, the glass is sent to its execution, the crusher. This is an enormous machine whose steel jaws or hammers grind entire bottles into small fragments with a deafening roar. The sound is as if thousands of chandeliers are simultaneously shattering. Several types of crushers exist: jaw crushers that crush glass between two plates, and hammer crushers where hammers spinning at furious speeds smash glass against a steel wall. This stage's goal is to transform bulky and fragile bottles into a uniform mass called cullet. This material is far more convenient for transport and, most importantly, for melting. At this stage, any remaining impurities not removed earlier can be additionally screened out. After crushing, the cullet is sieved through a system of vibrating screens that calibrate it by size. Even after crushing, cullet may contain microscopic metal or organic particles invisible to the eye, so it undergoes final, even more thorough cleaning. Magnetic separation here works at a new level, capturing the tiniest metal inclusions. Then special optical technologies are used to remove ceramic or porcelain remnants, which look like glass but have different melting temperatures and can cause defects in the finished product. This guarantees that absolutely clean material enters the furnace. Then the glass crumb is sent to vibrating sieves, where it passes through several levels of screens with different mesh sizes for separation into fractions. Different grain sizes are used for different types of products. This entire process is fully automated, minimizing risks for workers. After all stages of cleaning and calibration, the purest cullet is sent to the factory's heart, the melting furnace. At the plant, it's loaded into gigantic furnaces where it melts at temperatures from 1530 to 1650 degrees Celsius. At such heat, glass becomes liquid, viscous, and fiery red, like lava. Adding cullet to the melting process is not just ecological genius, but economic genius too. Recycled glass melts at a lower temperature than primary raw materials, sand, soda ash, limestone, which reduces energy consumption by 30%. Sometimes a small amount of new raw material is added to the melt to adjust the chemical composition and guarantee the strength and transparency of future products. After the glass transforms into a uniform liquid mass, its rebirth begins. The molten lava is directed into forming machines. Here, a drop of molten glass under air pressure transforms into a new bottle, jar, or vase in seconds. At large plants, this process is fully automated and can include high-precision molds to ensure perfect quality. Immediately after forming, the red-hot glass products pass through a long annealing tunnel, where their temperature gradually and very slowly decreases. This is a critically important stage that relieves internal stresses in the glass and prevents cracking. After forming and cooling, new glass products undergo ruthless quality control. Special robotic systems check every bottle for the slightest defects, air bubbles, micro cracks, uneven wall thickness, or incorrect shape. Optical scanners and lasers illuminate the glass, revealing flaws invisible to the eye. If a product doesn't meet the highest standards, it's ruthlessly rejected and sent back for remelting. Then, bottles are tested for mechanical strength, checking whether they can withstand the pressure of carbonated drinks and impacts during transport. Only after passing all these tests are new glass products packaged and dispatched to market. Thus completes one cycle of their endless life.